So a while back I made this 3D printed camera tripod using threaded rod from the hardware store and just machine screws, and it works acceptably well for something homemade like this, but it does have a major drawback, and that is to loosen and tighten the support, which allows you to collapse the tripod, the storage. You have to thread by hand this wing nut up and down about half a meter of threaded rod, and that is a big usability issue, so that's what I was setting out to solve with this project. I started just with a vague idea of what I wanted to do, sketching out the kind of degrees of freedom of the system, and just kind of went. I knew at the beginning that for the sake of compactness I would probably not want to use springs, but rather a live hinge, a built-in spring. But I still wasn't sure how I would maintain the degrees of freedom, or restrict the degrees of freedom to prevent the nut from slanting or slanting to the side. And it's very important that we don't do that, because cross-threading the nut risks damaging the threads on the legs. So it's very important that the nut either be fully engaged or not engaged at all, but it should be difficult to have it half engaged or slanted off to an angle. Be sure to make some jazz hands before you begin. So now I'm about to use the worst possible method to find the layout here, taking some cues from woodworking perhaps. I don't really know what I was thinking here. I completely ignore the center guide anyway. I just pick from my fancy selection of drill bits here, something which will be one size below the tap, ignoring of course the advice that you have from tapping charts. So that means this project is no longer aerospace grade, sadly. And here we are, showing off my wonderful set of taps. And if you don't know what a tap is, it's basically a tool which you screw into a hole that will cut out a thread profile for a particular size thread. So in this case it's an M4 thread that I'm trying to pick here. And this set is nice because it even comes with a screwdriver for when you give up trying to pull the threads out of the little plastic slots with your sausage fingers. And what I'm doing here using the drill, you should not do, you should do it by hand, but I'm lazy and I always find it really difficult to find the center when doing it by hand. So I'm willing to risk destroying my tap. Taps are very hard, but also very brittle. So to cut the nut in half, I start by filing down and then speeding up the footage so that nobody notices all the times the hacksaw slips off. Here, just cleaning up the threads with the needle file, and coming back in with the thread tool just to make sure the blowout isn't interfering with the threads of the split nut. Here's revision 1. I went with 100% infill and printed off this little lever mechanism with a bunch of support material as well. I just wanted to get this finished out of the printer as quickly as possible. And you can see my first mistake, not putting any preload on this. So it theoretically it fits, but it's got no tension holding it in there at all. And there it is. Yeah. Ah! Also, I'm not really a fan of this red filament. It really makes everything I print turn out looking like it's made of salami. I had thought that might be due to the fact that I was printing with 100% infill, so I thought I'd test something out. No, still salami. Revision 2 is looking pretty not bad. At least there's enough preload holding the nut in place. Unfortunately, when I designed the little retaining clip, I neglected to account for the fact that I would have to install it on the rod. So what I really recommend in this kind of situation, rather than printing something else, is just going at it with a hacksaw. Hacksaw and a bit of persuasion. Solution to all life's problems. This is often better than reprinting from scratch because it's faster, and you save plastic. And when you're in the prototyping phase, you don't really care about the final appearance anyway. And about 40 minutes of arduous installation later, unfortunately, this design is only supported at 2 points, and that causes it to tip and ratchet on the threads of the rod when you pull it up and down. So I had to revise that and come up with a thicker design that would be supported at 3 points. And while I was at it, I also filed down the washer just so we'd have clearance. This is probably not what I'll do in the end, but it was just a quick way to get things working. And I also used some scrap from a previous print project. I printed off a bunch of these spacers and didn't need all of them for a previous project, so I thought I'd put them to use here. I then printed off some levers. Once installed, I had to hone down the retaining clips by a little bit of careful machining. The main issue with this design is the lack of torque. You can only torque the nut about a quarter or a half turn before it cams off the threaded rod. So I had to look into a different design that would allow us to clamp down on the threaded rod, and that reminds me of a mechanism I have seen before. Now, if you allow me to get a bit pretentious here, I'd like to explain how I think about things like cams and springs. This is just how I do it. I have no idea if this is how you're supposed to analyze these kind of things. I find it helps to think in terms of potential. So you can view potential energy as height of something, basically. So if you imagine a ball rolling down a hill, the universe always seeks to lower the potential energy of things, right? So the ball always wants to roll downhill, entropy and that kind of thing. But the universe is stupid, fortunately for us, so we can outsmart it a bit by adding a little dip in the potential, like a little valley on top of a hill. So if we want something to stay in a high potential region, that's how we do it. Okay, alright, what am I going on about? Well, if we take the coordinate and the potential from this diagram, we can map them onto a cam and get something roughly equivalent. So if we view the compression of an open spring this time as the potential, and we can map the x-coordinate here onto the rotation of the cam, that allows us to trace out the profile for the cam. So if we imagine we are pushing the ball up the hill, so to speak, by compressing the spring, So we start in this uncompressed situation here, and then as we ascend this potential, the radius of the cam is getting greater and greater and greater. We're compressing, but then we have this little dip here, and that's what allows for the cam to stay stable. So that tells us roughly what shape we would expect. So here's the new version. This time I was sure to drill out all the holes except for the final part where the plastic could be used for the screw to thread into. And here is it with the cam, and as you can see it works pretty well. I went through a number of design iterations then on improving the cam so that I could latch it on the end of the clamp, and then I ended up with all these scrap parts. Here's the final design that I settled on, and after a bit of machining it runs quite smoothly up and down the shaft. It also clamps quite well and doesn't have the cam out problems that the other one did, so you can clamp down with quite a lot of force. Now just to take the component that I've painstakingly built over the last couple of days and move it from the outer rod to the inner rod where it's actually needed. No! So I've seen a trick on YouTube before. Let's see if this works. Yeah, okay, I think so. In all seriousness, I had intended to use a larger rod for the centre anyway. This small one is just a temporary fix. I just modified the design slightly in CAD and tweaked it physically as well by using a different screw, filing down, that sort of thing. And here's a final shot of me actually using the thing. There we are. It works. No longer taking up a huge amount of space in my living room. I hope that was interesting. I hope at least you learned some new information, and if not, at least it was entertaining to watch. So thanks for watching. See you in the next video. Bye.